Good day. Welcome to Study Unit 1. Study Unit 1 is on Chapter 8, which is on probability. And in this first part of Chapter 8, we are going to look at Section 8.1 up to Section 8.3. So you can turn to page 185 in your textbook, please. In STTN 111, you focused on descriptive statistics, where you had a data set and you wanted to order and summarize the data. So you created, for instance, frequency distributions for your data, or you calculated the mean for your data set, and you also represented your data graphically. But in STTN 121, we are going to focus on statistical inference, where we use sample data to draw conclusions about the whole population data. Because we do not always have access to the whole population, or due to financial constraints or time constraints, we can't observe the whole population. And probability is going to help us in the process of statistical inference because it provides the foundation for statistical inference. If you look at the outcomes in the study guide, you will see that there's 4 different things that we are going to focus on. First of all, we are going to look at set theory from mathematics, which forms the basis of probability, and that will help you understand the concepts in probability. So you should be able to understand the definitions and the notation of set theory. Then we are going to graphically represent sets and the relationships between sets with Venn diagrams, so you should be able to draw them. And then we are also going to look at the concepts of sample spaces and events. And then lastly, we are going to calculate simple probabilities. Probability is a numerical measure of the chance that some event will occur. So you've used probability in everyday life before and you might not have realized it. There's different terms that we use for probability. For instance, what is the odds that the Proteas will win a World Cup final? Well, not very good if you look at their track record. Or what is the possibility of rain tomorrow? Or what is the chance that an investment will be profitable? Like I indicated in the outcomes, we need to understand set theory and its notation before we can move on to probabilities. So the first concept that is important is the universal set, and it's denoted by this symbol, the omega symbol, and it denotes a set of all the elements under consideration. For example, if you look at alphabet letters, your universal set will contain all the letters from A up to Z, or if you look at digits, your universal set will consist of all the numbers between 0 and 9. Then sets within the universal set are points, and they are denoted by italic uppercase letters, for example A, B, C. Then we can list the outcomes or the elements within a set. For example, if we have set A and it consists of elements A1, A2 and A3, then this is the notation that we are going to use to indicate that. So you just separate the different elements within the set with commas and you put them in braces. Then Venn diagrams can be used to visually display the relationship between sets. If we want to indicate that one set is a subset of another set, for example, A is a subset of B, we use this notation, and then visually it can be displayed like this. B is a set within the universal set, and A is then a subset of B. So set A has some of the elements of B, but B contain all of the elements of set A. The union of sets A and B is denoted by this notation, A or B. And with unions, we look at all the points or elements that occurs in A only, in B only, or in A and B, if they do overlap. In intersections of sets A and B, we use this notation, A and B, and here we only consider the points or the elements that occur in both A and B. So where sets A and B overlap, the shaded region will contain all the points or elements that occur in both of those sets. The complement of set A is denoted by this notation, A superscript C. If I have a set A in my universal set, then everything that is still my universal set but not in set A, that will form my A's complement. For instance, let's say my universal set contains all the alphabet letters and set A consists of only vowels. Then all the other letters except my 5 vowels will be A's complement. And just take note then that A, the union of A and A's complement, will form the whole universal set. It's important that you can distinguish between mutually exclusive or disjoint sets and non-mutually exclusive sets. When sets are not mutually exclusive, it means that they overlap. So two sets will have some points or elements in common. But when I have mutually exclusive or disjoint sets, like in this case, then the two sets in my universal set will have no points in common, so they do not overlap. Then the intersection of sets A and B will then simply be a null set or an empty set, which is denoted by this symbol. For example, in an ordinary deck of playing cards, aces and kings will be mutually exclusive because if you draw a card, you can't have an ace and a king at the same time. But kings and hearts will not be mutually exclusive because you can have both at the same time, because you can draw a king of hearts, for instance. Let's do a class exercise on practicing drawing Venn diagrams. This is a numerical example. So for each set, I want you to indicate how many people will fall within each set, and if they overlap, how many people will fall in that overlap. So in the exercise I tell you, an IT firm has 12 programmers on staff. 6 of the programmers can program in Java, and that set is indicated by J. 4 of the programmers can program in Python, that set is indicated by P, and 1 programmer can program in both Java and Python. So now, before you draw the Venn diagram, you need to indicate whether the sets are mutually exclusive or not. Well, I tell you here in the question that 1 programmer can program in both Java and Python. So that means that the sets are not going to be mutually exclusive. So in question A, draw the Venn diagram for me to illustrate the situation. And then in B, I ask you to indicate how many programmers can program in Java but not in Python. And please ask the assistants for help if you struggle with this. Okay, so let's look at the answer. For A, I have 6 programmers that can program in Java altogether. But 1 programmer can program in Java and Python, so that's the easiest place to start. In that overlap, I'm going to have 1 programmer then. So in the Java only part, there will be 5. And since I have a total of 4 Python programmers, and there was 1 that can program in both Java and Python, it means that the Python only part will only consist of 3 programmers. So if you look at that union, it adds up to 9 programmers. So that means that since there's 12 programmers on staff, 3 will fall outside of that union. So there's still three programmers that's in my universal set, but not in that union. So those three programmers can program in C# or some other language, for instance. Then for B, how many programmers can program in Java, but not in Python? So it will be only this Java part. So that means it's 5 programmers. You can just take note of the distributive law and De Morgan's law. We are not going to apply this at this stage. We will use them later on when we do the laws of probability. All that these laws tell you is that you can write intersections and unions in different ways and still get to the same points or elements. For example, if I write that intersection as the intersection of set A and the union of sets B and C, I will get the same points and elements if I write the union of those two intersections. Or an example of De Morgan's law, if I have the complement of sets A and B, and I take the union of those complements of those sets, I will get to the same element. We can then now move on to the basic probability concepts on page 190. So the first concept that you should take note of is an experiment. So in probability theory, you conduct an experiment to make observations or take some measurement that leads to a collection of outcomes. So if you toss a coin, for instance, you want to see what the outcomes of your experiment will be. Then if you have a collection of all those possible outcomes in the experiment, we denote that by the omega symbol, and we call that our outcome space or our sample space. For example, the outcomes when you toss a coin will be heads or tails. If you roll a die, your outcomes will either be a 1, 2, 3, up to 6 that you can get on that die. If you play a soccer game, you can win, lose, or tie the game. If you weigh a person, your outcome will be X, such that X will be any real number between 0 and 300, provided that the person does not weigh more than 300 kilograms. In probability theory, an event is a subset of the sample space, and similar to sets in set theory, it's represented by uppercase letters. So, for example, let's say that my experiment is rolling a die. This will be my sample space, and we define event A as the event that an odd number occurs. Then it means that my outcomes in event A will only consist of 1, 3, or 5. So event A has occurred if any one of those possibilities comes up on the die. You should also be able to list outcomes for multi-stage experiments. Multi-stage experiment is an experiment that you repeat more than once. A useful tool in listing outcomes for multi-stage experiments is a tree diagram, which can help you. For instance, it's easy if you toss one coin, then your outcomes is heads and tails, for instance. But to help you indicate the outcomes for 2 coins or 3 coins, etc., this can be a useful tool. So in this class example, I tell you, a coin is tossed 2 times and the sequence of heads and tails is recorded. List the outcomes of the sample space. We can let H denote heads and T to denote tails. Then our tree diagram will have 2 branches for the first toss. Since you have 2 outcomes for your first coin, you can either have a heads or a tails. For the second coin, you have 2 possible outcomes again. If the first toss was a head, your second coin will either be a head or a tail. If your second your first coin was a tail, then your second coin can also have a head or a tail. Then we simply read off our outcomes from the top to the bottom. So my first outcome will be heads, heads. My second outcome will be heads, tails. My third outcome will be tails, heads, or my fourth outcome will be tails, tails. And then we just list the outcomes in our universal sample space. Either of these notations are correct, and this is the one that the textbook use, but you can use this shortcut if you're working with letters, because the letters are clearly distinguished, but this notation won't work for numbers, for instance. For example, if I want to list the outcomes on 2 coins, and let's say I have a 1 and a 1, then that will indicate the first outcome of 11, and that's different from a 1 and a 1. But you're welcome to use it for letters. In example 8.1, they show you an example of a tree diagram that will have 3 levels. So they tell you there, according to the Bureau of Census, 50% of all homes in Potchefstroom are heated with gas. For 3 randomly selected homes in Potchefstroom, list the outcomes of the sample space corresponding to whether they are heated with gas or not. Also list the outcomes which make up the following events. So they want you to list the outcomes for those 4 events. So we can let G denote that the randomly selected home is heated with gas, and N that a home is not heated with gas. So for the first home, you have 2 possible outcomes. The home can be heated with gas, or it cannot be heated with gas. Then for the second home, you will have 2 branches branching from that first home, because you have 2 possible outcomes for the second home each time. So if the first home was heated with gas, the second one can be heated with gas or not. If the first home was not heated with gas, the second home can be heated with gas or not. And then for the third home, you will have 2 branches again each time, since you also have 2 options for the third home each time. And then again, you can just read the outcomes from the top to the bottom for all 3 homes. So you will have 8 outcomes in total for your sample space. Listing the outcomes for the events then. Event A was defined as exactly 2 of the 3 heat with gas. So there you will look at all the outcomes in your sample space where you have exactly 2 G's. So it will include those 3 outcomes. For event B, it's defined as only 1 heats with gas. So from your sample space, you will include all the outcomes where you have 1 G in that event's outcomes. So it will consist of those 3 outcomes. Then event C, all 3 heats with gas. So from your sample space, you will only have this one outcome because you look for 3 G's. And then for event D, at least one of the 3 heats with gas. At least tells you 1 or more. So it will include all the outcomes except for none of the homes heating with gas. So your turn. You can complete this class exercise for me, please. I tell you that Belani and James can do 3 different dances, a waltz, a tango and a samba. And for a competition, they must decide in which order they want to do these 3 dances. So we can let W denote waltz, T tango and S to denote the samba. So for question A, I want you to list the outcomes of the sample space, and for B to list the outcomes for these 2 events, please. So event A is the event that I do the waltz first, and B is the event that I do the samba before the tango. Okay, let's look at the answer. For the first dance, there's 3 possible options. But then for the second dance, there will only be 2 possible options each time, because if they did the waltz first, they can't do the waltz for the second dance as well. So there they can either do the tango or the samba then. If they did the tango for the first dance, they can only do the waltz or the samba for the second dance, and if they did the samba for the first dance, they can only do the waltz or the tango for the third dance. For the second dance, sorry. And then for the third dance, they will have 1 option each time, because if they did the waltz and the tango for the first and second dances, they can only do the samba for the third dance. If they did the waltz for the first dance, the samba for the second dance, then they can only do the tango for the second and for the third dance, etc. So you will have 6 possible outcomes for your sample space. And if they do the waltz first, these will be the 2 outcomes for event A. And for event B, they do the samba before the tango. So you will have those 3 outcomes. You can complete exercise 1 for homework, please, and the exercise solution will be available on eFundi. The definition of a probability is given on page 193. So a probability is a numerical measure of the chance that an event will occur. There's 2 types of probabilities that we get. First of all, subjective probability. And that is the probability that an event will occur based on an educated guess, expert opinion, or intuition. For example, if a doctor estimates the survival rate of a patient after surgery, or a climatologist that predicts the weather conditions. But those probabilities can't be verified statistically. The second type of probability is objective probability, and it's also called the classic interpretation of probability. And that's applicable to random or stochastic events that cannot be predicted with certainty. But the relative frequency with which they occur in a long series of trials is stable. Okay, so that means that we can use the relative frequency to calculate that probability. And if you think back of STTN 111, the relative frequency was given by the frequency divided by n. So your frequency is just the number of times that a certain event occurred, and n will be the total number of times you did the experiment in this instance. So it can be verified statistically. For example, if you roll a die a number of times, then your relative frequency will stabilize at 1/6 or 0.167 or 16.667% for each outcome of the dice, because each number on the die will have a chance of 1/6 of occurring. Obviously, you don't have time in class to throw a die thousands of times, so I simulated the experiment in Excel for you to illustrate this concept. So I rolled a die each time for a couple of times, and then I recorded the outcome each time. So if I did 10 repetitions, you can see that the relative frequency is not that stable, but the larger the number of repetitions, then the relative frequency for the different options on the die stabilizes. So for 10,000 repetitions, for instance, that you can see that the relative frequency for each of the values on the die is more or less 0.16. On page 194, you can see the characteristics of probability. It's important to keep these conditions in mind when you do calculations, because your answer always needs to adhere to these conditions. Okay, so first of all, the probability of event is always between 0 and 1. The closer the value is to 0, the less likely it is that the event will occur. The closer the probability is to 1, the higher the probability is that the event will occur. If the probability is exactly equal to 0, that event will definitely not occur. But if the probability of an event is equal to 1, then that event will definitely occur. Then also the second probability, the condition of a probability is that the sum of the probabilities of all the outcomes in a sample space is always equal to 1. Okay, so for example, if you toss a coin, the probability that you will get a head is 0.5. The probability that you will get a tail is also 0.5. So if you add the probabilities of all those outcomes, it will be equal to 1. Usually we work with equally likely events. That means that each outcome has the same chance of occurring in your sample space. But irrespective of whether you're working with equally likely events or not, this is the formula that we use to calculate probability for an event. So the probability of an event A is equal to the number of outcomes in event A divided by the number of outcomes in the sample space. For example, if you draw a lotto ball, the chance that you will draw a particular ball will be 1 over 49 on the first draw. If you do not replace that ball, the probability that you will draw a ball on the second draw will change to 1 over 48, etc. An example 8.3 on page 194, they tell you 10 people, 4 men and 6 women are in a meeting. At random, they select a person to preside. What is the probability that the person selected is a woman? So we can define event A as the event that a person selected is a woman. So that means that the number of outcomes in event A will be 6 and the number of outcomes in our sample space is 10. So the probability of event A occurring will be 6 over 10 or 0.6 or 60%. There's another example on page 194. They tell you suppose students that are registered for the first semester are randomly assigned to 6 sections of introductory English course. What is the probability that the student is assigned to an odd numbered section? Okay, so the possible outcomes in your sample space is 1, 2, 3, 4, 5 or 6 since there's 6 sections, and we can let event A be the event that the student is assigned to an odd numbered course. So that means that the outcomes in event A is going to be 1, 3 or 5. So the probability that event A will occur will be 3 over 6 or then 0.5. In example 8.5, they tell you, in a certain game, a participant wins on the first roll a pair of fair dice if the sum of the total of the two dice is 7 or 11. Calculate the probability that he wins on the first roll. Okay, so in total, you will have 36 outcomes in your sample space because you have two dice. And you can have, for instance, a 1 and a 1, a 1 on the first die, 2 on the second die, 1 on the first die, 3 on the second die, etc. We let event A then be the event that the total is either 7 or 11 on the die. If you look at the outcomes in event A then, all the ones in green will be the outcomes for a total of 7, and the outcomes in pink will be those for a total of 11. So you will have 8 possible outcomes in event A. Since there's 36 in the total sample space, That means that your probability that event I will occur will be 8 over 36, or then 0.222. In example 8.6, they ask you to calculate the probabilities of the events in example 8.1, where we had the different randomly selected homes that we wanted to see whether they are heated with gas or not. So we had 8 outcomes in our sample space. So the probability of event A will be 3 over 8, or then 0.375. Your probability for event B will also be 3 over 8, or then 0.375. Your probability for event C will only be 1 over 8, or then 0.125, and the probability for event D will then be 0.875, or 7 over 8. For exercises, you can do exercise 1. I want you to add a question there, please, where you calculate the probabilities for the events. And then on Venn diagrams and probabilities, you can complete exercise 4. You can do these in class. If there's time, or the exercise solutions will be available on eFundi. And please, if you struggled with any of the content in part 1 of chapter 8, please come and consult with me. Thank you. That's the end of this session.